Okay, so one of the great things about Haystack is we don't just have people from the industry side here, we have people from the academic side. And our next speaker is Sean MacAvaney. Have I pronounced that right? Marvelous. He's currently at the University of Glasgow, where he's a lecturer and assistant professor. And he's a researcher developing new techniques for using AI in search engines. And he's going to be talking about rethinking, reranking. So without further ado, Sean MacAvaney.
Hello, everybody. Thank you for the lovely introduction. I'm Sean MacAvaney. I'm a new face around here. I don't recognize many of you, and I'm sure I'm a new face to you guys too. So just a little bit of background on myself. As was introduced, I'm Sean MacAvaney. You can find me on Twitter or X with my surname there. I'm a lecturer, assistant professor at the University of Glasgow. And my research mostly focuses on very practical-oriented research within information retrieval. So if you've heard of techniques like learn sparse expansion, the kind of thing that Slade uses in order to add tokens to documents or queries, things like search results evaluation using large language models, so you don't have to do as much labeling, document quality prediction, so you don't need to index garbage, and the topic of today's talk, which is adaptive re-ranking. I'm happy to chat with you about any of these topics or other things as well. Let's start off talking a little bit about what re-ranking is. We had a nice introduction earlier today on a lot of the pipelines and processes that you can go through. But I want to take a little bit of a separate twist on this by kind of rethinking this whole process. So typically what a re-ranking system would look like. First, you would have some user query. User enters in tablet or something into the search engine. You run your retriever. Maybe that's BM25 for lexical search or fancier vector methods to get some list of results over your data set. And this is an okay ranking, but maybe not so great all the time, right? So especially if you're doing something like lexical search, there can be a lot of problems in how these results are ranked. So what you'll often want to do is you often want to use a re-ranker, something that uses a model like BERT or GPT or anything like that, in order to hopefully find a better order for these search results. And hopefully at the end of that, you get some new awesome ranking of these results, right? So using our fancy large language models and so forth, you're able to really understand the content of documents, really understand the intent of the query, hopefully, and put these documents in a much better order. Now, there's a problem with this process, though. You start off with millions and millions of documents. You narrow that down. You filter that down to maybe hundreds of documents. And then you essentially use the re-ranker to pick what top 10 documents or so you end up showing the user. But if you miss a document when doing retrieving, you start off with millions of documents and you miss this golden document here that doesn't quite meet the filter, you'll never have it down here to re-rank, right? You lose it completely, right? If it's a product that you're searching for, you never get it. To address this problem, people have thought about all sorts of solutions, and the typical go-to place to address this recall problem, as you would call it, is to focus on the retriever. It's a natural place to look. The retriever misses something, so you want to fix the retriever so it doesn't miss those things. I've come up with all sorts of great approaches for doing this: sense retrieval, learn sparse, hybrid, et cetera, in order to try to enhance this pool of documents that the re-ranker gets, that you don't miss what you're really looking for. Now, what I would argue is really what we wish we could do is we wish we could run the re-ranker just as a ranker over the entire corpus, right? We have millions of documents. We really trust, maybe GPT-4o Mini's assessment of search result quality. We really would like to score every single document, and then we would for sure get that gold document at the top, no matter what, assuming it's the best document and your ranker is able to identify that. Of course, this is just way too costly. Obviously, doing all this inference, it costs a lot of time. If you're using GPT-4, it would cost a lot of API credits and so on. Now, the next best option, I would argue, is to give the reranker access not just to the list of initial search results that you get from your retriever, but also access to the whole rest of your data set, the whole rest of your corpus. Now, this seems like the same thing as this, right? But actually kind of leveraging this initial set of results is super, super powerful in order to kind of unlock a lot of the other documents in your corpus. It seems crazy, but I'll show you how this can be done with minimal cost. So basically with essentially no extra cost. How it can not just improve re-ranking methods, like using GPT-4 or whatever, but also retrievers like Colbert and others. And on top of that, it's ready to use with open source tools and so forth for you to start using today, if you like. I promise I'm going somewhere with this, but let's talk about the game Battleship. Who knows the game Battleship? Yes, seems like most everybody. That's good. I asked around a little bit, and in German it's Schifferverschenken, and in Spanish it translates to sink the fleet. Anyway, hopefully you have some familiarity with this game. I used to play it as a child. It's kind of fun. Basically, the idea is that you're playing against an opponent who has a secret board, right, where they have a bunch of ships. You know that they have some long ships and some short ships, all laid out on kind of this coordinate grid. But of course, you don't see that board, right? Your board starts off completely empty, right? So you don't know where the ships are. But your goal is to identify the positions of all your opponent's ships, right? So you want to figure out that. For instance, the long ship there is from B2 to B5 and so forth. The way that you do this is you first just make a guess, right? This might be a reasonable guess. You don't really know anything about your opponent's board initially, so you make a guess. You ask your opponent then, is this a hit, right? So it's as if you're launching a strike into the ocean. For some reason, you don't actually have any intelligence about the actual positions of the ship, but let's ignore that limitation of the game. You ask your opponent if it's a hit. It turns out this one is a miss. There's no ship there. Maybe then you make another guess, and that happens to be a hit. So you ask your opponent, F2, is that a hit? Yes, it is a hit. Now, once you know that that's a hit, the way the game works at least, you don't sink the ship immediately. You need to guess all the positions of the ship. And at this point, you actually learn a lot about where the ship might be, right? You know that they can only be oriented kind of vertically or horizontally. So you know that the ship, there's absolutely, certainly, one of the other positions of the ship is in one of these coordinates with the question mark at this point. So maybe you guess one of them, that happens to be a miss. You guess another one, that's another hit. And then you kind of iterate on this process to find the complete ship. Okay, so what does this have to do with ranking? Well, I would argue that when you're doing re-ranking, you essentially think of these initial list of results that you get, reasonable guesses, as kind of guesses on this board, right? So maybe you have documents 1, 2, and 3 at these particular positions. And instead of asking, your opponent if your document is a hit or a miss, you're asking your re-ranker, right? You're saying, is this a good document? Is this a bad document? Where does this go in the ranking? And your re-ranker gives, some new information, right? So maybe this document up there at position C7, that's now the first top ranked document. That's a really good document for this query. And this one over here at E5 is not so great. Now, what's crazy to me is that in normal re-ranking, you just stop right here, right? You learn all this stuff about which documents are good and which are bad, and then you just show these to the user, right? If I was playing Battleship right now, that would be a terrible strategy, right? I would basically miss all the ships. If I wanted to find all the positions, I would need to just keep on guessing randomly until I find all of them. So we've actually learned a lot of information about what makes a document relevant to this query, right? By identifying a document that is relevant, that's considered relevant by some really strong model like GP24. Adaptive re-ranking is this approach where we kind of leverage this information that we gained from these high-scoring documents to find other ones that were missed by the retriever. So we don't necessarily need these documents to come back in that first set of guesses. We just need something that gets us roughly close. And we can kind of then explore the area around it. So maybe we send these 4 other documents that are adjacent to our fancy re-ranking method. Some of them are not so good, right? You know, we're just kind of using the proximity here to kind of guess what might be a good document, what might be a bad document. But we find another one, and that kind of gives us even more information about what's good. And we iterate that process, so on and so forth. Does that make sense? Yeah? Okay, the next question is, how do we decide which documents are worth checking, right? So when we have a coordinate system in Battleship, right, there's characteristics about the shapes of the ships that we can leverage. We know things about how, the lengths of the ships and how they must be kind of oriented on the game board. In ranking, we don't have that exactly, but we have something similar. So one option would be to, once we kind of identify a document that we think is really good, we could issue that same document as a query back to our engine and take the top results for that query, right? So we treat this document that we have as a query and find the most similar other documents to it. If this is a good document, documents that are similar to that are probably also good. This goes to a bunch of IR theory from Van Rijsbergen and deals with the cluster hypothesis and so on. But in a practical sense, the idea is that a similar document, a document similar to the one that you think is good might also be good. We don't know for sure, but we'll use the re-ranker to tell us if it's actually good. This is a really, really bad idea. It's really slow. You don't want to have to actually execute, look up your document, maybe even encode it as a, new query executed against the engine, all that. Really bad, really slow. That's a terrible idea. Won't be practical in the slightest. But it is still the right idea, at least in my opinion, right? Because you're able to kind of leverage the information that you get from this document and say, I want documents that are kind of along this line, right? I think this is a really good result, but what are the other good ones there? What can we do better? Well, we can leverage something we actually already have, at least in most vector databases. We can leverage this k-nearest neighbor graph that we've built for doing vector search, for using HNSW search. We already have this graph that says, here's a document, here are similar documents to this. And we already use this to do search over vectors, right? This graph kind of already establishes this proximity. It's as if it's that coordinate system from Battleship. It's super fast lookups, right? So you're able to immediately, just by your document identifier, you're able to see, these other 6 documents or 100 documents or however you set it are similar or related to this. And it's constructed completely offline. So you're not really incurring any costs at query time, right? You already have this data structure ready to go. All right, so that's the idea. How well does it actually work? First, a few technical bits. Being a scientist, I got a caveat with all this stuff, right? We do things like fix the re-ranking, what we call the budget, which is the number of documents that we're sending to the re-ranker. So we're not comparing a system that re-ranks 100 documents with one that re-ranks 1,000 or something like that. No, all of these systems are re-ranking the same number of results. So that cost is fixed. In our adaptive setting, we just take a really simple approach of taking basically half the results from the first stage and augmenting it with the other half of results that we'll score from this proximity graph, right? So we'll look up the best documents and kind of iterate on that process. In terms of, does it work? We'll measure NDCG for the overall ranking quality and recall, which is, in this case, the percentage of relevant documents retrieved. And we test on a variety of different re-ranking pipelines, re-ranking systems. Okay, so here we have a graph. We have recall at 1,000 on the x-axis there. So how many of the relevant documents have we found? And NDCG on the y-axis. And here's just a set of initial retrievers, right? So we have BM25 there with lexical search. We have an augmented BM25 called doc2query. We have TCT, which is a vector search, and we have Splayed version 2 plus XYZ, whatever, up there. Very, very strong, right? It's getting high recall and very good search results. Now, putting a re-ranker on top of this, right? Let's try re-ranking our lexical search results, our BM25 search results, using a re-ranking model. Here we're using Mono T5, but we tested this across a whole bunch of different ones. And as you would expect, when doing just regular re-ranking, it improves the overall search result quality a ton, right? NDCG improves substantially, right? From what, 0.6 to 0.73, right? That's a pretty big jump. You're getting a lot more of the best results at the top of the list. But recall doesn't change, right? It's a vertical line, right? You're not finding any new documents that you had before. When you apply this adaptive approach on top of that, you shoot all the way over there, right? So not only are you further improving the overall quality of the top results, but you're finding a whole lot more of the relevant documents for this query. And what's actually quite remarkable is the recall is doing better than something like a vector search would, right? By kind of leveraging your cross-encoder, leveraging your re-ranker to try to find the best results, you're doing better than you would have had you done some fancy semantic search to begin with. Still not quite at Splayed. But of course, you can also run re-ranking on top of any of these other systems, right? So you can re-rank and adaptively re-rank on all of those too. And you see pretty consistent results in terms of improving the overall search result quality and the overall efficiency. And this isn't re-ranking kind of any it's not like you're re-ranking 1,000 documents when you previously were ranking 100, right? The costs are basically fixed, right? You're still re-ranking the same number of documents. You're just being smarter about which documents you're re-ranking. And the process of looking up these documents is really, really cheap, right? It's all computed offline. So the cost is basically fixed across all of these. This doesn't just work on weird academic Mono T5 re-rankers. I tried it on Cohere's cross-encoder model when they released one a while back. And yeah, we see similar situation, right? So, that not so visible on this display, but we can see NDCG is increasing, recall is increasing, etc. All right. So in summary there, we found that kind of this nearest neighbor graph exploration really helps re-ranking models, neural re-ranking models. And by focusing on the neighbors of the top scoring documents as we're ranking, like we're playing Battleship, right? Finding the similar positions to the ones we already know are good. This helps prioritize documents that are more likely to actually be relevant. We have a whole bunch of other findings and stuff, and there's a conference paper on it if you want to read. Okay, let's go on to retrievers. Let's talk about retriever models. So the adaptive approach that I was talking about up to this point, it actually involves two strategies. We focused mostly on this first part, so scoring documents near the best ones we found so far. That's essentially the adaptive bit of adaptive re-ranking. The second bit, and it was a little subtle about this before, but now it's really important, is the re-ranking bit. It says we're going to start off with good, but really inexpensive guesses about what are good documents. So we're not just randomly guessing on the board for Battleship, right? We have some good guesses about where the ships might be, right? Where the good relevant documents are. So the intuition of the next part of this talk is can we leverage the same strategy, starting with good but cheap guesses? Can this also help dense retrieval models? And it turns out they can. So HNSW, hopefully you're all familiar with this. This is one of the approximate nearest neighbor algorithms, and it's commonly deployed in a whole bunch of different engines. HNSW actually kind of applies this random strategy as if you were just kind of randomly picking on your Battleship board, right? You randomly subsample nodes from one version of your hierarchical graph to the next, and then you search kind of the opposite way back down. So you start off essentially searching and scoring random documents and kind of iterating on this process to find slightly better and better documents as you go. until you're kind of at the lowest level, and then you find the most similar results there. So HNSW kind of takes this random approach, right? As if you're just kind of randomly guessing and then narrowing in from there. Can we leverage instead this initial cheap set of search results that we can get with just a simple lexical search for very low cost? Can we use this instead to kind of help seed this search process, right? So instead of navigating through this hierarchical graph and looking at this and looking at that and scoring all the way down, can we instead start off by picking some of those nodes, right? So the green and blue don't show up particularly well here, but picking some of these nodes here and starting off with those to kind of seed our search instead of the hierarchical approach instead. And once we do that, once we know which documents are the best from this initial pool of results from something like BM25, we're able to then kind of iterate on that process to continue to find better and better documents. So kind of shortcutting this whole hierarchical approach of HNSW. Okay, so how well does this approach work? Well, here now we're most interested in two things. On the y-axis, we're interested in the overall search result quality, so NDCG. And on the x-axis, retrieval latency. So this is milliseconds per query, searching over around 10 million short passages. This is a standard information retrieval benchmark, a pretty standard and dense retrieval model, and this is using a single core of a CPU. So it's just single-threaded, this whole process. As a point of reference, if we did an exhaustive search on a GPU over all these vectors, something way more expensive than a single core of a CPU, that would get us this line here in around 65 milliseconds. So beyond the scope of this with way more compute. HNSW is really strong, right? So we're able in 5-6 milliseconds up to 8 milliseconds to do a really strong approximation of that of the full results. Get very strong results of in the top of our ranking, and we can vary kind of how long we're willing to take on this process by changing some of the parameters of HNSW that say how much of the graph you're willing to explore. There's other approaches too, but they don't work as well. Now, if we just re-rank, so in our first talk today, we heard about kind of this re-ranking approach where you can take BM25 and just re-rank using our vectors instead. That actually eclipses HNSW in most of these settings just by choosing a different number of search results to re-rank. So re-ranking itself is already really strong. And then if we do this adaptive approach, where we're looking at the neighbors and prioritizing the neighbors and seeding kind of this the search of our graph using the neighbors instead, that does even better. And it turns out that it can do even better than an exhaustive search, right? Even better than scoring everything. We're finding more of the best results for our queries. We found that this doesn't just work on these single representation dense vectors. This also works on something like Colbert. So at SIG-IR this year, we presented this paper where we tested out using ladder, compared it with re-ranking and this algorithm called PLAID, which is this bespoke engine specifically made for Colbert to try to find kind of the best results. And again, we see similar findings to what we saw with the single vector representations. We're able to do substantially better basically at any operational point that we choose. Okay, so in summary on the second part, adaptive re-ranking ideas can improve retrievers too, not just re-rankers. So rather than just focusing on these kind of expensive language model re-ranking techniques, we're able to leverage them kind of at the initial search side too to get better results. And it applies to both single vector and multi-vector dense retrieval models we've seen. Of course, other findings, blah blah blah, conference papers. You can look at these if you're keen. Okay. On top of that, these techniques are open source and ready to use. So they're not just an idea of an academic in an ivory tower or something like that. these are ready for you guys to use today if you like. So we have at the University of Glasgow, we have this platform called PyTerrier, which kind of lets you glue together all these different components in different ways. There is an adaptive re-ranking and ladder component in PyTerrier to let you play around with that. It could also be used with the re-rankers package. So if you're familiar with this from answer.ai, is that it? There's this nice package with re-rankers. You can use it with that too. I've got a fork of re-rankers, but I'm gonna make a pull request at some point when I get around to it. So hopefully that makes it into the core re-rankers package there. We're working on adding a ladder to Lucene. The Lucene maintainers seem positive to it, but you know they can be a bit picky, right? So you know, still working on my way through that, but it seems promising there. So hopefully at some point this is ready to use kind of directly in Lucene. There's a corresponding issue on Solar. And Joe Burgum says that you can also do this in Vespa. So if you're using Vespa too, you can add a custom searcher implementation that applies ladder. All right, how am I doing on time? There'll be sufficient time for questions. In summary, adaptive re-ranking, we find that this improves the quality of search results at a pretty minimal cost. So by kind of leveraging offline computation and this idea that similar documents are close to one another, we're able to improve the quality of search results, find more of the relevant documents, basically with adding almost no overhead. It works for both re-rankers and retrievers, and it's ready to use with open source tools. I'd like to thank my collaborators on many of these works. So Craig MacDonald at University of Glasgow, Nicola Tolomoto at University of Pisa, Hrishikesh Nasli and Ophir at Georgetown University helped collaborate on many of these projects. So thank you. And are there any questions?
Fantastic. Thank you, Sean. I'll just say, when you're talking about getting this into Lucene, what you need to Lucene committer. Any Lucene committers in the house? Shh, he says, hiding in the corner. But yes, there are some people here who could probably help with that, which is one of the wonderful things about this event. So do we have any questions for Sean? First one over here. Come to you a bit later.
Hello. First of all, thanks for the amazing talk, really inspiring. Am I right that if I would pick not BM25 for my domain, maybe an even better one that retrieves the initial docs, I would even come higher in the benchmarks, right?
Yeah, so let's see if we go back. Uh-oh. Excuse the scrolling here. Right, so kind of the core results here were with BM25, right? So using just a simple lexical search, improving and getting better results. But yeah, no, we've seen that if you have a stronger initial stage, you still see improvements. This is ultimately bounded by how good your re-ranker is, right? So in this work, we're using Mono T5. There's even better ones today that distill down GPT-4 and stuff like that. So I imagine you could get even higher. And as you find more better results, hopefully that helps you find even more of the results too. So I'd expect it to go both up and to the right using other better first stages.
Thank you. So we've got a question online. I'm going to ask you this, but we may also need the help of someone in the room. Why does Vespa need a custom searcher? Can rank profiles solve it?
Oh, I think that's a question for Joe Burgum.
Where is Joe? Where are you, Joe? There you are. Okay, so I'm going to take this to Joe.
Yeah, thank you for a great talk, Sean. Yeah, you cannot do like you can do a lot of different things in Vespa ranking profiles for sure. And you can express a sparse retrieval, a BM25 or whatnot, and then re-rank using an adaptive model. But the logic of re-ranking, and then figuring out, hey, this was a good hit, and then expanding the search, the visual interface, that requires a custom logic, which is in Vespa is done in a custom searcher. Yeah.
Great. That's Desianis, I think. Thank you. I hope that answers your question. So next, coming over here, come to you here.
Thank you for the great talk. Maybe I missed something, but I think you mentioned at some point the cross encoder as your re-ranker. And if that was the case, it is unclear to me how you build the graph of products.
Right. So the question is, you're using a cross encoder to score, and normally when you're building a graph that say, these documents or these products are similar to these other ones, you're using the same thing that you're scoring to build up that graph. Yeah, that's a detail I glossed over, so I apologize for that. But it turns out it doesn't matter so much what you pick, right? So we tested both using kind of lexical similarity, right? So issuing the query, building this offline, but issuing the document as a lexical query over BM25, and semantic similarity, so kind of encoding them as dense vectors and looking up documents that are similar based on that. It all seems to work, right? So as long as there's some notion that this document is similar to this document, this is an idea in academia that we call co-relevance, right? So the document that is relevant to, that is also relevant to the same kinds of queries. If you have some connection like that to build this up, that's all you really need. Maybe it's even something like, we haven't tested this on web scale data or anything like that, but maybe it's something like link structure, right? So you have products that may be linked to other products. Maybe you could use that structure to say, maybe this is something else you'd like to look at if you think this document is relevant. So kind of anything that can get at this, if you think this is relevant, this might also be a good thing to look at. That's a great question.
Thank you. So we don't have any more questions online at the moment, so we have one more here.
Yeah, so first of all, a great idea, something new I learned today. So have a question in the first part where you said you're using a cross encoder, and then say the cross encoder is telling you this is the first great document, and then applying an ANN search for that particular document to find the similar documents. Are there any lessons that you learned in terms of setting thresholds for that particular, like only the top quotient scores of this particular similar to this particular document? Because if you do a KNN search again, it's gonna give loads of documents, and then that's gonna again hurt your the final grade of relevance, right? So is there any lessons learned on that threshold levels that you said for the ANN search?
Yeah, so we found that it's largely robust to kind of the K that you're using in your KNN, right? Going super low means it's not searching much of anything, right? So you're not really searching enough of the neighbors. So you don't want to set it to like 1. Also, yes, if you set it to 1,000 or something, now you're no longer letting it explore to new areas, right? So yeah, we found anything kind of in the range. There's a graph in the paper, but I think it was something like anything in the range from like 4 to 16 neighbors per document tends to work out nicely. But that might kind of vary on the domain and application and stuff too.
Thank you.
Yep.
Any more questions? Yes, there's one over here.
Hi. How many iterations do you usually do between retrieving, re-ranking, retrieving, re-ranking?
Right. So basically, we tested off. We tested this by kind of setting a fixed budget. So we say we're willing to re-rank 100 documents, for instance, right? And kind of the iterative process is going batch by batch. When doing this kind of processing for a cross encoder, you need to batch these documents anyway. You can't really encode 100 on a regular size GPU directly. So we just used the batch size we were already using to score the documents, which I believe was something like 16. And then we just kind of alternate between the two modes, right? So initially you pull from the top results from BM25, you score those. Then you look up the neighbors of those top results, score a batch of 16 from those, and then back to your initial ranking, right? So anything that you haven't yet scored from that initial set, you go to the next 16 and score there. So kind of alternate between those two modes. Does that make sense? Okay.
I think so. Okay, do we have any other questions for Sean in the room? Okay, so next Haystack, we're expecting implementations. We'd like some practical stories, please.
Absolutely.
Yeah, but thank you very much, Sean.
Thanks.